In this lecture, I'd like to talk about simultaneous move games. I want to talk about defining what a simultaneous move game is, modeling it, how we model it, analyzing the possible outcomes, and finding the equilibria. In a simultaneous move game, it's really this, in game theory, we can break game theory into two types of games. Sequential move games, where one player moves, the second responds, and so on. Or the second type of game, which we're talking about here, is a simultaneous move game. Each player moves simultaneously without knowing the other player's move. Now, it could be that they are literally moving at the same point in time and therefore don't know what the other one is doing. It could also be that they're not literally moving at the same exact point in time, so exactly simultaneously, but the key piece here is that each player moves without knowing the other player's move in advance. And so one of the ways that we analyze, or the standard way that economists will analyze simultaneous move games, is using a matrix or reduced form of the game and using that reduced form to identify the Nash equilibrium or the multiple Nash equilibria associated with the game. Recall that a Nash equilibrium is a set of strategies, one for each player, in which no player has an incentive to change strategies given what their opponent is doing. In other words, each player is doing the best that they can. Let's look at a two-player game. Each player's payoffs are modeled here in this table and matrix by assigning player 1 to choose row strategies. So we see that player 1 can choose 5 different strategies, 1, 2, 3, 4, and 5. Player 2 can choose also 5 strategies, which we've labeled A, B, C, D, and E in the columns. And then the actual payoff to each player is found in the cell where the two strategies intersect. Player 1, the row strategies are listed first. Player 2, the column strategy payoffs are listed second. So, for instance, if player 1 is choosing strategy 1 and player 2 is pursuing strategy A, the payoff would be given by the intersection in the upper left cell, 9 for player 1 and 9 for player 2. The way we will identify the Nash equilibria here is by going through very deliberately and asking, given or assuming that one player is making a certain choice, and asking what is the other player's best response to that choice. For example, let's suppose that player 2 is pursuing strategy A. If player 2 is pursuing strategy A, what would be player 1's best response? Well, if player 1 chooses strategy 1, the best response, or the payoff rather, to player 1 would be $9. If player 1 chooses strategy 2, their payoff would be 7. Strategy 3, the payoff would be 5. Strategy 4, the payoff would be 3. And strategy 5, the payoff would be 1. If player 2 is choosing strategy A, player 1's best response is strategy 1, and so we place an underline. We're going to do this in blue here for player 1 under that payoff in the cell 1A, so that upper cell with the 9, 9 payoff. We're going to do this for each of player 2's 5 possible strategies. For instance, if player 2 is choosing strategy B, we could ask again, what is player 1's best response? And we see, looking down column B at the blue payoffs for player 1, the payoffs are 7, 5, 3, 1, and 9. 9 being the highest payoff, that corresponds to strategy 5. So we would conclude that if player 2 is pursuing strategy B, strategy 5 would be player 1's best response. We underline that cell associated with strategy 5. If player 2 is pursuing strategy C, we look down the column, 5, 3, 1, 9, 7. 9 is the highest payoff associated with strategy 4 for player 1. We underline that. If player 2 is pursuing strategy D, again we look down column D at player 1's possible responses and payoffs, 3, 1, 9, 7, 5. 9 is the highest payoff associated with strategy 3, so we underline that. If player 2 is pursuing strategy E, the payoffs for player 1 associated with strategies 1, 2, 3, 4, and 5 are 1, 3, 1, 5, and 3. Strategy 4 is the dominant strategy or the optimal strategy. We underline that. Now, we're going to switch and do the same thing, only going across rows. Let's examine each of player 1's strategies, each row, and select the column strategy that maximizes player 2's profits. For example, in row 1, if player 1 is pursuing strategy 1, player 2 could pursue strategy A, B, C, D, or E, and the payoffs would be 9, 1, 6, 4, and 1. 9 is the highest payoff, and so strategy A would be player 2's best response if player 1 is pursuing strategy 1. So we'll put another underline there, this time in red for player 2, and we'll do the same thing for all of player 1's strategies. If player 1 is pursuing strategy 2, what is player 2's best response? Well, player 2 could respond with strategy A that would lead to a payoff of 8, strategy B that would lead to a payoff of 2, strategy C that would lead to a payoff of 6, strategy D that would lead to a payoff of 4, strategy E that would lead to a payoff of 3. Strategy A would be player 2's best response given that player 1 is playing strategy 2. So we underline under the 7 and 8 that cell indicating that A is player 2's best response. If player 1 is pursuing strategy 3, we see that the possible payoffs for player 2 are 6, 3, 8, 7, and 5. 8 is the highest payoff, which is associated with player 2 choosing strategy C when player 1 is choosing strategy 3. Say that 10 times quickly. We underline the 1 and the 8 there to indicate that C is player 2's best response. If player 1 chooses strategy 4, player 2 can obtain, let's see, well, now this is interesting. Player 2 can obtain a payoff of 9, which is the highest possible payoff if player 1 is choosing strategy 4. And there are actually 4 different ways they could do that. So we're underlining here column A, column B, column D, and column E for player 2. All of those choices lead to a payoff of 9 for player 2. And lastly, player 1, if player 1 is choosing strategy 5, player 2's possible outcomes are payoffs of 2, 8, 7, 6, and 7. 8 is the highest payoff associated with strategy B. To find the game equilibria, and I say equilibria, which is the plural of equilibrium, because the equilibria, or the most likely outcomes, are those outcomes where we have double underlines, where both of the players have underlined that cell. The reason that these are the equilibria is because the double underline indicates that that cell, or that set of strategies, has the property that each strategy is the best response to the other. So we see here that this game has 3 equilibria, where each player is responding optimally to their rival. Player 1 could pursue strategy 1 and player 2 strategy A. So 1, A is one of the equilibria. 5, B is a second equilibrium. And 4, E is the third equilibrium. In each of those instances, we can see that those sets of strategies are best responses to the other. Now, which of those individual strategies would be more likely? Without a little more structure, we can't necessarily say, but we can say that those 3 outcomes of the 25 outcomes listed are the only 3 that are stable, meaning if we get to that point, neither player has any type of strategy to deviate from those strategies, and so those will be the most likely 3 outcomes to arrive at and stay at. Thanks for listening.